This is the elastic force as a conservative force, part three. We're going to derive an expression for elastic potential energy. So we know how much energy is being stored by a spring with a particular stiffness when it is stretched or compressed by a particular amount. To do that, we're going to start with Hooke's law for spring force. We have Hooke's law plotted here on a graph of spring force as a function of displacement x. And there's that linear relationship with that negative slope where the slope represents the opposite of k, the spring constant, the stiffness. So here we're showing a spring that starts out compressed by a certain distance x1, and then that'll be moment one. And then it compresses further to a final compression x2 at moment two. As it compresses more, the spring force that it exerts on the cart that's pushing on it increases. So we see for a small compression, the spring pushes back with a small spring force. For a bigger compression, the spring pushes back with a bigger spring force. And we can imagine this cart here, say, slowing down as it compresses the spring. Its kinetic energy is being transferred into spring potential energy stored in the spring here. So then, how much of its kinetic energy gets stored in the spring? Well, that's related to the work being done by the spring force. The work is transferring that energy from kinetic into potential forms. We can find out how much work was done by looking at the area under the curve, or the area between the curve and the zero axis on this force versus displacement graph. All right, so that area will be this trapezoidal region here, colored magenta. So to find the total work done by the spring between those two moments, we'll need to find that area. We'll break up that region into a rectangle, this rectangle here, and a triangle, this triangle here, and add up those two areas. The area is below the zero axis, so we expect that it represents a negative amount of work. Negative work makes sense because we are removing kinetic energy and converting it to spring potential energy, or elastic potential energy. All right, so now some geometry here. First, the area of the narrow rectangle there. That'll be its width, x2 minus x1, times its height, which will be minus kx1. So that's this expression here for the area of that rectangle. Then the area of this little triangle here, 1/2 base times height. So 1/2 times the base will be x2 minus x1. And the height of this triangle will be minus kx2 minus kx1. So that's this expression here, 1/2 base times height for that little triangle. And now some algebra. I'm going to factor out a minus k term from each term. Factor out a minus k from each term in the expression, pull that minus k out front. Then distribute the x1 across these two terms. So we have x1, x2 minus x1 squared. That's those. I'm going to leave the 1/2. And then this becomes x2 minus x1 times x2 minus x1 once we factor out the minus k. So we'll distribute across those two terms to get this expression here. Distribute the 1/2 across these. And once we do that, we have a couple of terms that we see will cancel out. This and this will cancel. We have a 1/2 x1 squared minus x1 squared, which gives us a negative 1/2 x1 squared. So we've simplified down to here. And if I then distribute the spring constant k, the stiffness, back once again, we've managed to make the work done by the spring force between moments 1 and 2 look like the opposite of the difference between the final value of this quantity, 1/2 kx squared, and the initial value of that quantity, 1/2 kx squared. This is perfect for us because we know that the work done by that spring force should be equal to the opposite of the change in the elastic potential energy. That's the negative work done by the spring, converting kinetic energy into stored elastic potential energy here. So if this is the opposite of the change in spring potential energy, or elastic potential energy, You see, we use those two terms pretty interchangeably, spring and elastic potential energy. If it's the difference between these two terms, then we are invited to define 1/2 kx squared as the elastic potential energy US of a spring interaction with stiffness K and displacement X, where X can be a compression or stretch. So there we have it, 1/2 kx squared for spring potential energy. We see that based on this definition, it can never be negative. X gets squared, K is always positive. So unlike gravitational potential energy, which can be negative, spring potential energy or elastic potential energy is always positive. So we've written that the work done by the spring equals the opposite of the final US minus the initial US, the opposite of the change in spring potential energy. And we see that since this is a conservative force, the elastic force, according to Hooke's law, is a conservative force, the work that it does is path independent. The work that it does depends only on the initial value of displacement and the final value of displacement, not the path taken. That is, the work done by the spring can be found from this expression, depends only on x2 and x1, not any of the x's in between, not how long it took to get from x1 to x2, not how many times the mass perhaps oscillated back and forth before arriving at x2. Nothing about the path matters, only the initial position and the final position. That's path independence for the work done by a conservative force.